Okay, welcome to GADAPS. So today we have Amin Gholampour, who is going to talk about two-dimensional stable pairs and fourfolds. Okay, Amin?
Okay, thank you very much for having me speak in your seminar. So this is a joint work with Yunfeng, Jiang, and Jason Low. Here is an outline of my talk. I will start reviewing some major curve theories, curve counting theories for threefolds, and then I will emphasize more on one of them, Pandharipande-Thomas stable pair theory. And then the reason is that our work is about basically one-dimension higher generalization of their theory. So, okay. So let X be a non-singular projective. Let's see. So let X be a non-singular projective variety over complex numbers, and beta be a class in H2. Then counting curves of in X in class beta is an old problem. So here are some classical examples. So for example, we all know that the number of lines in a cubic surface is 27, and here are a few more complicated problems. So these two problems, so the problems of counting curves in Calabi-Yau threefold is related to and inspired by a string theory. Okay, so to in order to get the formation invariant answers for such enumerative problems, we need to have two things. So compactification of the modular space of curves in X in class beta, and also the transversality of the solutions. To obtain compactification, we need to allow for some curve to degenerate. So we need to have singular curves. We need to allow for some sort of singularities in the boundary. And also for transversality, so instead of perturbing, in algebraic geometry, we get the transversality by means of the virtual fundamental class of the modular space. So the virtual fundamental class can be thought of as the actual fundamental class of the perturbed modular space, which is of expected dimension inside the actual modular space. Okay, so one of the curve theories that I want to talk about is Donaldson-Thomas theory. So in here, we assume that X is a threefold. So in Donaldson-Thomas theory, compactification is achieved by considering the Hilbert scheme. So the modular space that we have is the Hilbert scheme of one-dimensional subschemes of X in class beta. So in the Hilbert scheme, so all sorts of singularities basically are allowed. So the curves can even become reducible, non-reduced, and have embedded components, zero-dimensional components. Another curve theory is Gromofitan theory, in which the compactification is achieved by considering the modular space of stable maps from nodal curves to X. So we already allow the domain curves to have singularities, multi-singularities. And in addition to this, so the maps are also allowed to, they need not be embedding, so they can be multiple cover of their images in X, and also they can have contracted components. So another curve counting theory, Pandharipande-Thomas theory, I will talk about in more detail. But because of these complications that we have to allow in the boundary of the modular space to compactify, so basically these deformation invariant numbers, which are called DT invariants, Donaldson-Thomas invariants, Gromofitan invariants, so on, they may differ from the actual counts of curves. So they are called the virtual count of curves in class beta. Okay, here are some examples of the generation of curves in the Hilbert scheme. So in the first one, a family of conics degenerates to a double line. And in the second one, so we have a family of rational twisted cubics in P3 that degenerates into a nodal plane cubic with an embedded point at the singularity. And we can also further degenerate into a non-singular plane cubic plus a point. So in Gromofitan theory, we can think of this as a family of, so the analog of this is a family of embeddings with image is this curve inside X, and when, so then it degenerates to a double cover of a line. And in this example, so again, we have a family of embedding into P3, given by these rational twisted cubics that they degenerate to, so the stable map becomes, so they are embedding, but in here, the map become not one-to-one at the singular point. Okay. But this one doesn't occur in, for example, in Gromofitan theory, this sort of thing. Okay, so now let's talk about the third curve counting theory. Was introduced by Pandharipande and Thomas. So again, it's a so Gromofitan theory is works for all varieties of any dimension, but Donaldson, Thomas, and Pandharipande-Thomas are only for threefolds. So fix a projective non-singular threefold X. So a Pandharipande-Thomas pair, a PT pair, consists of a one-dimensional sheaf, pure one-dimensional sheaf. So pure means that doesn't have any zero-dimensional subsheaf, and a section, a global section. And in addition, we require the co-kernel of the map induced by S from OX to F to be zero-dimensional. So the meaning of the co-kernel condition can be interpreted as F is the push forward of a line bundle outside of a zero-dimensional subset of its support. So support is a curve, so you can imagine a line bundle on the curve, then we push it forward into the threefold. So outside of a zero-dimensional subset, this sheaf is a line bundle. An example, so we can make a stable pairs this way. In fact, so if C is a non-singular curve and L is a line bundle on C, and S is a non-zero section of L, then basically we can push this data forward and get a PT pair on the threefold X. So in fact, if the support of the sheaf F is non-singular, all the stable pairs are obtained this way. But the support can become singular. So in general, the support can become singular, but so it's at most a Cohen-Macaulay curve. So meaning that the depth of the structure sheaf at any point is 1. So in particular, C cannot have so C can be non-reduced or even reducible, but it cannot have embedded points. So something that we saw in DT theory, gaining embedded points not allowed in PT theory. So this is one advantage of this compactification. And we cannot have roaming points either, right? So points cannot move off the curve. So everything is just restricted to the curve under consideration. Okay, so if we go back to that picture, so the analog of a PT pair in here is just, you can think of the structure sheaf of this curve, and then we have a map from OX to the structure sheaf. So we have a surjection from OX, so that can be taken as a section of OC, and then the curve just degenerate to a double line. So basically, in here, the co-kernel of the pair is 0. But in here, so again, we can think of this as a surjection from the structure sheaf of X to the structure sheaf of the curve C. But when it degenerates, suddenly so we don't have, remember that in PT theory, we don't have any embedded points. So what happens to make up for this is that the map from OX to the sheaf is not surjective at this point. So the co-kernel, so we have a co-kernel at this point, so non-trivial co-kernel at this point. And again, this does not occur in PT theory.
I mean, does this enhancement of curve with this sheaf structure and section is discrete? I mean, if I fix the curve, there will be some finite number of enhancement that you are taking, or it can be also a continuous family.
Yeah, it's a continuous family. It can be continuous family. Yes, yes. In general, yes. Okay. Going back. All right, so now let's talk about how the moduli space of PT pairs is constructed. So as I said, I explained this in more detail because then when I talk about our pair theory, so it's the construction is parallel to this. So to construct the moduli space of stable pairs, so let's fix a very ample line bundle omega on X, and also fix a polynomial Q with a positive leading coefficient. Now suppose that we have a pair of a one-dimensional sheaf and a section. So the Hilbert polynomial of f with respect to omega is given by this formula. So CH2 is the second Chern character of f, so which is the class of the support of f. And the leading coefficient of this Hilbert polynomial, so it's a degree 1 polynomial because f is one-dimensional. And the leading coefficient is given by this. So we define the notion of stability. So the construction is parallel to construction of the moduli space of Giesecke stable sheaves. But because of this, because we're having a pair of sheaf and section, so yeah, there's some modification to account for this section as well. So then we say a pair F and S is omega and Q. So the stability depends on the choice of these polynomials and the line bundle that we fixed. So if F is pure and for any non-zero proper subsheaf G, so we require these inequalities to hold. So there are two possibilities: either S factors through G, so S is a section of F, so you can imagine we have a map from OX to F. If this map factors through G, then we use this inequality. If not, then we use the above. And if in addition, so as in the case of sheaves, so if or vector bundles, so if we have if equality never occurs, then we say that the pair is stable. So what Pandharipande-Thomas showed was that if we choose this polynomial very large with respect to data of the sheaf F, the class of the Chern classes of Chern characters of the F that we fix before. And so if Q is very big, then in fact, semi-stability becomes equivalent to stability and becomes equivalent to PT stability. So what was PT stability? Recall that PT stability is basically the purity of F and also zero dimensionality of the co-kernel. So then suddenly everything becomes simple if Q is chosen to be large. So in particular, so the stability becomes independent of omega and Q. All right, so then going back to the general picture, Lepotier construct a moduli space of pairs that in general, depends on omega and q. So it's a modular space of stable pairs having fixed Hilbert polynomial. So it's a projective scheme over C. So it's always a fine modular space. And so by the result of Pandharipande-Thomas that I just quoted for Q sufficiently large, so this modular space does not depend on the choice of omega and Q, and is just simply denoted by Pn x beta. All right, so then we come to, so now that we constructed the modular space, we come to the question of transversality, so construction of the virtual fundamental class. So for this, we need to study the obstruction theory of pairs. So first, think of a pair F comma S as a two-term complex where OX sits in degree -1 and F sits in degree 0. So then the obstruction theory of such pairs is governed by these X groups. So X0, X1, and so on. So this means that so there is an obstruction class. So this is a general thing in obstruction theory of anything, basically. So there is an obstruction class in X1 whose vanishing is equivalent to the existence of infinitesimal deformation. And then when the obstruction class is 0, so the deformations are basically, they form a torsor for X0. So there is a problem with this obstruction theory, though. So it's not useful for constructing the virtual fundamental class. And the reason is that there are also higher obstructions. So X2 may not vanish. So to construct virtual fundamental class, we need to have a two-term or perfect obstruction theory. So the idea of Pandharipande-Thomas is that instead of considering the obstruction theory of pairs, so they look at the obstruction theory of the two-term complex in the derived category. So they consider the fixed determinant deformations of I, so the two-term complex. So they show that the deformations of F as a pair coincide with the fixed determinant deformations of I. And as a result, the modular space of PT pairs that we talked about is a component of modular space of complexes in the derived category. Then on the other hand, the obstruction theory of perfect complexes in the derived category, say with fixed determinant, is governed by this X group. So 0 stands for the traceless. And the reason is that we are fixing the reason for taking the trace-free part is that we are fixing the determinant. And then the advantage is that this one is non-zero only for I equal to 1 and 2 and can be used to construct the virtual fundamental class using the Behr and Fentaki technique. So this gives us, so then we get a virtual fundamental class in Chao group of Pn in this degree, where Vd virtual dimension is the difference of these two non-zero X group, which is constant for any I in the modular space. And then by Riemann-Roch, it can be calculated to be minus Kx, the canonical bundle times class of beta, the second Chern character of F. Okay. Then, so the invariants, so the invariants are defined by integrating against this class. So if X is a Calabi-Yau threefold, then there are further simplifications. So Kx is trivial, so therefore the virtual dimension is 0, and then the PT invariant, depending on n and beta, basically is the degree of this virtual class. There are so some brief history, so highly non-trivial relations among.
So I mean, so in this case, these numbers are automatically integer, not like the
Yes,
other
the reason
ones.
is that so in Gromofitan theory, so the modular space is Doleman for a stack, so that this is the reason that we see rational numbers. But in DT theory and PT theory, the modular space is a scheme, so all the invariants are integers. Yes, so there are relations among these invariants. So again, for Calabi-Yau threefold, so the virtual dimension on all the three theories is 0, so we can just take the degree of the virtual fundamental class. But the modular spaces are completely different than the virtual class. But yeah, so to talk a little bit about how these the relations are. So we put this into generating function. So we fix beta and then we sum over all n. And also we do the same thing for dt and Gromofitan invariants. So U keeps track of the genus of the domain curve in Gromofitan theory, and n keeps track of the Euler characteristic of the ideal in DT theory, and also in here it also keeps track of the Euler characteristic, holomorphic Euler characteristic of F in PT theory. So the first part of the conjecture is that these generating functions, so ZPT and ZDT, after dividing by some power of Machmann function, are Laurent expansion of rational numbers in Q, which are invariant under this involution Q to Q inverse.
Where is beta here? What is it?
What is delta?
Beta.
Beta is so beta is the class of the support curve in PT theory. So
yeah, but in the conjecture, beta disappears. I don't know.
Yeah, so in Gromofitan theory, beta is the class of the image of the curve, and in DT and PT theory is the second chain character of the basically underlying sheaves. Oh, sorry, I dropped beta. Yeah, you're completely right. I'm sorry. Yes. So Z beta. So it has to be Z beta PT, Z beta DT. I'm sorry. Yes. Sorry. And then the second part of the conjecture says that if we make this change of variable, which is now allowed because of these the first conjecture, so basically this generating, we have this equality between the generating functions. So, sorry about that. I drop all the betas in here. Sorry, you're completely right. So here are some brief history about what is known. So this conjecture was formulated by Malek, Nekrasov, Okonkov, Pandharipande, and also Pandharipande-Thomas, Pandharipande-Thomas. And then it's proven in a lot of cases. So in toric cases, so DTPT correspondence is proven for Calabi-Yau threefold using motivic. So the conjecture also holds for non-Calabi-Yau threefolds, but it's just a little bit more complicated to state, but it's very similar. So we have the same change of variable in particular. So they used, so the proof of Bridgman uses the motivic Hall algebra, so that if I have time, I'll talk a little bit about. Pandharipande-Pixton gave a proof of Gromofitan PT for Calabi-Yau complete intersections. Toda formulated higher rank version of DT and PT correspondence, and so on. Any questions so far?
I mean, I remember that in the Gromofitan case, one takes the sum over betas. I mean, if beta is ranging in one dimensional or one, I have to say, rank one module, like quintic. But in this case, you fix beta and you are taking the sum over the other.
Yeah, so for the sake of conjecture, yeah, so we have some other partition function that you sum over both genus and beta. But for the conjecture, we fix beta in both sides.
Okay.
Yes. Yeah. Okay, so now, so talk a little bit about what we did in the last section. So now we increase the dimension of X by 1. So consider a fourfold and fix a line, very ample line bundle omega again. And fix a chain character vector. So since we want to, our objects are two-dimensional inside the fourfold, so the chain character will look like this. So we start with 0 and 0. So the rank are 0, and also the first chain class is 0. Then assume that gamma is an effective class. Okay, so now everything, as you see, is parallel to PT theory. A two-dimensional stable pair in class CH consists of now a pure two-dimensional sheaf where the chain character of F is fixed, and S is again a global section of F. And now our stability is that the co-kernel of this, the co-kernel of S is at most one-dimensional. So in PT was zero-dimensional, and here is at most one-dimensional. So everything is, the dimension is increased by 1. So this time, by the co-kernel condition, we can think of F as a push forward of a line bundle outside of a one-dimensional subset of its support. So support is two-dimensional. And so again, as an example, if S is a non-singular surface in X and D is an effective divisor, then we can easily construct a pair as above, a stable pair as above. So the pair of a line bundle of the line bundle that is formed by this divisor and its canonical section, it will be so after pushing forward will give us a stable pair. So this is analog of stable pairs that we talked about in PT theory when the support is non-singular. But there is another degree of freedom in here. So we can also consider a zero-dimensional subscheme in D with the ideal I sub Z. Then S factors through the subsheaf IZ twisted by D of that line bundle. And this time we can again push this data forward to X and get a stable pair, two-dimensional stable pair X. And this time the co-kernel is the ideal of Z inside D. So I sub Z is the ideal of the zero-dimensional subscheme in S, but we can also think of its ideal as a subscheme of D. So the co-kernel is this ideal, which is a pure one-dimensional sheaf. And again, now, so all it can be shown that all two-dimensional stable pair on X with non-singular support are the form of example 2. But again, in general, so the support of F can be singular. This time, it need not be a Cohn-Macaulay surface, so it satisfies Serre condition S1, but not necessarily S2. But in PT theory, so the purity just implied Cohn-Macaulay condition. But if it happens that the support is Cohn-Macaulay surface, then the co-kernel is always pure one-dimensional. So in here, it is at most one-dimensional, so it can have zero-dimensional components. But if the support happen to be Cohn-Macaulay, then it's nicer. The co-kernel is just pure one-dimensional. As we saw in this example too, the support is pure one-dimensional. Okay, so now I can talk about the stability and so on much more quicker because it's just very similar to PT theory. So we need to we again to construct a modular space. We work with a limit of Laplacian stability. So when this polynomial that we fix is very large with respect to the data of CH that we fix. So we get a fine modular space that doesn't depend on omega and Q again. So we have a parallel result of Pandharipande-Thomas. And the modular space is again a projective scheme over C. So then, so as in PT theory, we are interested in identifying the modular space, the Laplacian modular space, as a modular space of objects in derived category. For two reasons. So for studying wall crossing, and also later on when one wants to construct the virtual fundamental class for this modular space. So for this reason, again, we think of 2D stable pair as a two-term complex in derived category, or x in degree -1, f in degree 0. And so in terms of the cohomology of this two-term complex, so the -1 cohomology is a rank 1 torsion-free sheaf. And H0 is at most one dimension. So H0 is basically the co-kernel of the section. So it's at most one-dimensional for our pairs. And then other cohomologies are 0. Then we show that there is a part of a T structure that contain all these two-term complexes. So this heart is explicitly given as follows: is extension closure of, so basically it's a tilt of the torsion pair given by sheaves that in X that are of dimension less than or equal to 1, and sheaves that are of dimension greater than or equal to 2. So you tilt this torsion pair and you get this sort of T structure. So all these J belong to A. To construct modular space of objects in derived category, we need to have some notion of stability as like analog of Giesecke stability for sheaves. So it's called polynomial stability, constructed by Bayer. So it's a variation of Bridgeland stability. So if you think of Bridgeland stability as Mumford slope stability, then polynomial stability of Bayer can be thought of as analog of Giesecke stability. So the polynomial, so to have a polynomial stability, we need to have a polynomial stability function that goes from the Grothendieck group of isabelian category A to polynomials with complex coefficients. So it takes E in here and sends it to sum over rho I powers of omega I, the very ample line bundle that we fixed, and the chain characters of E. So where these rho i's are some vectors in complex plane that are arranged this way. So the picture in the left side. So if I make, sorry, the indices are a bit too small. So this is minus rho 2, minus rho 3, rho 0, rho 1, and minus rho 4. So it has the property that the ZP of E for X sufficiently large, so they belong to semi-open upper half plane for any E in the heart A, and they satisfy the Harder-Narasimhan property. Then we say E is ZP stable if the argument of ZP of E prime is less than or equal to ZP of E for X sufficiently large for any proper non-zero sub object of E prime of E. So then what we prove is that, so the relation between the Laplacian modular space and the modular space of objects in derived category. So if we make this arrangement of vectors, then the ZP stable objects of A having a trivial determinant and chain character So the reason is that the Chern character in here is slightly different, is that now is the Chern character of J. So since we have this OX term, so it contributes this -1. So and this OX sits in degree -1, so that's why we have a -1 in the first component of the Chern character. So it's basically the same thing. So ignoring this, so we have again that gamma, beta, C, which are the Chern character of F. So okay, so then the P stable objects of A are exactly 2D stable pairs in class CH. And there exists a fine algebraic space, a moduli space for these objects, and then we have isomorphism of moduli space. So the Lapotier moduli space is coincide with the moduli space of objects, stable objects in derived category, given this stability. So this picture, so if we have a different arrangement for these vectors rho i's, then we get the stability for basically ideal shifts. So the Hilbert scheme stability, basically, that corresponds to the relation between PT and DT theory that we talked about. So let Zi now be the polynomial stability function corresponding to this arrangement in the right. Then the Zi stable objects of A. So we proved that the Zi stable objects of A having trivial determinant and Chern character as before are exactly the shift of ideal shifts by 1 of 2-dimensional subschemes of X. And the moduli space of Zi stable objects is identified with the Hilbert scheme of 2-dimensional subschemes of X in class H. So these two moduli spaces are recovered by using polynomial stability. Then the question is, how can we relate them? So in fact, there is so we can think of a wall crossing between these two moduli by changing the arrangement of these vectors. So going from this arrangement to this arrangement gives us some wall crossing phenomenon. So we have also higher rank versions of these two theorems that analog of TODA higher rank versions of PT and DT. Okay, so now I want to talk about, so then the question is how one can interpret this, this wall crossing. So we don't have interpretation in terms of numerical invariance, but we have two interpretations, one categorical and then one that lead us to a Hall algebra relation. So if you remember, so the Bridgeland proof of PT-DT theory in Calabi-Yau case was also based on Hall algebra techniques. So we first obtain the Hall algebra relation and then we integrate them to get the relation among the numerical invariants. So, all right, to talk about the categorical relation, so let's fix some notation. So for any two full subcategories C1 and C2 in the derived category, define bracket C1 and C2 and double bracket C1 and C2 to be full subcategories consisting of objects E that fit into these exact triangles, in which E1 comes from C1 and E2 comes from C2. And in the second case, in the double bracket case, we have no non-trivial homomorphism from objects in C1 to objects in C2. Some further notation. So if we have a torsion pair in co less than or equal to 1, so this is the category of coherent sheaves on X, of sheaves with support of dimension at most 1. So let mu be a real number and T and F be a torsion pair. So for example, this can be a torsion pair, 0-dimensional sheaf for torsions, and this is the torsion free sheaves of pure dimension 1. So this is an example of a torsion pair in co less than or equal to 1. Okay, so fixing mu and this torsion pair, then we can introduce this again full subcategory of objects in D, which are basically complexes concentrated in degree -1 and 0, such that H -1 of E is So it's mu omega semi-stable torsion free with a slope mu that we fix, and H0 belongs to this torsion part of the torsion. And there are no non-zero homomorphism from objects in T2E. Okay, then we have a technical result that if we have two torsion pairs, then satisfying T1 contained in T2, then we have this relation. So basically, you can commute these two factors. So basically, in this is as if in this exact triangle, so we are switching the role of E1 and E2. Then we conclude two special cases is when our torsion pair, the first torsion pair, the first one is T1 0 and F1 is the whole thing, and the second one T2 is just so T and F is just some arbitrary torsion pair. Then it's always satisfy this property T because 0 is contained in any. Then so we have this relation. So this co-T mu that we introduce in here, and this co-mu is just the semi-stable sheaves of slope mu. This then shifted by 1. Then the second corollary is that for any real number b, we have this. So again, this is obtained by so specializing this. So if we take T1 to be this subcategory, so this consists of those one-dimensional sheaves, at most one-dimensional sheaves, in which G is semi-stable with respect to this slope function, and the slope belongs to this interval I. Okay, now if we have these two relations, so now we want to go back to our relation between 2D stable pairs and ideal sheaves. So this category, we can show that consists of exactly our 2D stable pair. So basically, this condition says that the co-kernel is at most one-dimensional. We are fixing the determinants. So this means that we are fixing the determinants of this pair. And this is the rank, which is -1 as before, and the class gamma is pair. So basically, if we fix this data, then the objects in this are precisely the 2D stable pairs with these fixed data. And also co-0. So 0 means that the slope is 0. So the index 0. So mu is 0. And so this one are precisely the ideal sheaves of two-dimensional subschemes of X. Okay, oops. So now, okay, so in corollary 1, if we take T to be this category and slope is 0, and in corollary 2, if we set B equal to 0 and mu equal to 0, and if you restrict to this -1 OX gamma data, then we get this relation among our the objects that we are interested in. So, okay, so this one that you see in here corresponds, as we said above, corresponds to ideal sheaf of two-dimensional subschemes. And this one that you see in the second line corresponds to the stable pairs. And these two extra categories, so basically, or three. So these are three categories that they play the role of relating these two. Then we have some boundedness results. So we want to. So basically, these were our categorical relation among these objects that was motivated by this wall crossing between the polynomial stabilities. Then we have some boundedness, so we would like to interpret this as a relation in all algebra. So maybe I have time to get there. So suppose that gamma is a reduced effective class as before. So for some reason, technical reason, we need to assume that gamma is now reduced, is a reduced class, such that we also assume that any pure two-dimensional subschemes of X in class gamma are Cohen-Macaulay, so they satisfy S2. So we saw that it is possible for pure two-dimensional subschemes to be S1 but not S2. So we fix a class gamma satisfying this property. And then for such classes, we can interpret these two categorical relations as all algebra relations.
Can you give examples of gamma? Because for me, if you give me gamma to verify that these conditions are satisfied, it's almost impossible.
Yeah, I mean, you can, for example, gamma if, so if, for example, you are inside P4, I mean, it is not difficult to have some gamma. So if you are, for example, inside P4, take the class of a plane, then all the...
Yeah, but for X is Calabi-Yau, no?
We are not assuming Calabi-Yau fourfold in here. So it's for any fourfold so far. So
okay, it's for any fourfold.
Only used when we want to talk about the virtual fundamental class that I haven't gotten to. So far, everything works for any fourfold.
Okay.
Yeah, so so let me pass through this quickly because they are technical and they may not be so eliminating. So, but the idea is that all right. So first we say that the following subset of Q are bounded from below. So all possible. So we are fixing gamma in the Chern character, but then CH3 and CH4 can vary, right? So we are saying that for all two-dimensional ideal sheaves, basically the omega times CH3, this subset of Q is always bounded from below. So these are all two-dimensional ideal sheaves. So, ideal sheaf corresponding to the two-dimensional subschemes in class whose second Chern character is minus gamma. And similarly for the 2D pairs, so these subsets are bounded from below. But then if we also fix beta, the third Chern character, then we want to have some boundedness on the fourth Chern character. So again, so these subsets are bounded from below. So these are all objects such that the third Chern character is fixed to be beta. And so in these three categories that appeared in that categorical relation in the previous page. So the last one is bounded. So it's turned out that for this category, it's bounded from both below and above. For ideals, it's bounded below. For 2D pairs, bounded above. But for this extra one, it's bounded from both sides. Then we define these numbers. So minimum of these numbers that are bounded from below and so on. Okay, so a little bit about Hall algebra. So for the Hall algebra, so we have to work with a different heart. So this heart also comes from the torsion pair. Co bigger than 0 correspond. So back then we had the torsion pair based on the dimension of support. In here we have torsion pairs based on the slope. So in here the notation is introduced. So these corresponds to all extension closure of all coherent sheaves that are mu semi-stable and the slope is less than or equal to 0. And this one corresponds to the ones that having slope bigger than 0. So they form a torsion pair. Then again, you tilt it, we get the heart of a P structure. So A0 again contains all the objects of these few categories that we talked about. Let obj be the A0 be the stack of objects in this category, this abelian category, and obj sub CH be those subsets of objects with that have Chern character CH. So let HA0 be the motivic Hall algebra. As a vector space it is spanned by the isomorphism classes of one morphism of stacks from M to ob0, where M is a finite type, and with affine geometric stabilizer. So these are technicalities that one need to assume to construct this. And so this vector space is modulo some relations. The Hall algebra is this. So for example, we have a cut and scissor relation, and we have relation if we have a geometric bijection between two, say M1 and M2, then their classes in the Hall algebra are the same. And again, if you have Zariski vibrations with same fibers, then again we have the same classes in Hall algebra and so on. So we have this Hall algebra now, and H sub CH is again consists of those objects such that M to ob factors through ob such CH, basically objects that have class CH. So it has a modular structure, so a Grothendieck group of stacks over C. So using just the product. It is also more important, it is also equipped with a associative product star that is obtained by means of short exact sequences in A0X. So this is a definition of a product. So very quickly, since I'm going out of time. So also this is also equipped with a product, associative product. So let me just get to the result because it's only 1 minute left. So we go to the completion of the Hall algebra. So we introduce two completions using those numbers bounded, using the boundedness result that we had. We define these numbers, and this allows us to define these two completions. Then the following membership holds. So then to each category that we had in the few pages back, we have an object in the Hall algebra that are denoted as follows. So for example, delta bigger than 0 sub C correspond to this subcategory, and it belongs to this completion. So yeah, so one go through those boundedness result, and one can show that this membership holds. So to each of these objects that appeared in that page, we have these objects of the Hall algebra. Then this is our the Hall algebra relation that we get. Basically, those two categorical relations can be shown to be translated into these formulas in Hall algebra. So in PT theory, Ridgeland showed just one relation among delta P and delta I. So there were no delta T needed, but these delta C appeared in his relation. And then it was possible to basically integrate those relations to prove the conjecture of Pandharipande-Thomas. But yeah, so we didn't have enough technique to get to the numerical invariance. So I didn't have time to talk about this last section about the symmetric obstruction theory that basically uses the result of O and Thomas. So the technique of Beran and Fantaki doesn't work for two-dimensional PT pairs, so the objects in Calabi-Yau fourfold. That was working for threefolds, but not for fourfold. And the reason that it was that even this obstruction theory is not perfect, so it has three terms. But the point that it is symmetrical, so we have Serre duality relation, and this basically allows us to use O Thomas to construct a virtual fundamental class for in case that X is a Calabi-Yau fourfold for the moduli space. But as I said, so we weren't able to find the numerical relation using this Hall algebra relation between our the invariance that one gets this way. Okay, so I'll stop here. Thanks for listening.
Okay, thank you, Amin. Usually there is no. Okay. Roberto, can you stop recording? Just a moment.